Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. Today we're in physical science class. I marked you out, Ty. Y'all are working it out. Okay. This is physical science class, and we're going to talk about our new unit, energy. So, what is energy? This was your warm-up. It's the ability to cause change. Who remembers the symbol for change or difference? It's a shape. Not a circle. It's a triangle, yes. So change, oops, I got drawn out of race. To cause change. If you don't remember, that's the Greek letter delta. It means change or difference. And if you don't remember that, write it down. Don't just put a triangle that you don't understand. So, or to do work. So in our standard here, we have a new standard. You're supposed to know the types of energy, and they are chemical, mechanical, electromagnetic. Remember we studied that before. Ronald McDonald is very ugly, extra gross. Light, we studied that before. Roy G. Biv. Sound, thermal, electrical, and nuclear. Those are written here in the standard, which are also written on your paper. So if you don't like copying it here, you can find it here in the standard on the next bottom of the next page, and they're listed there also. So these are types of energy, and we've already talked about a lot of these. We talked about nuclear last unit. We talked about electromagnetic. We talked about light. We've talked about chemical energy. We saw all of those forms of energy exciting electrons. And so you can see that even though we're taking a little break from chemistry and we're pivoting to physics, it's all related. We have a unifying concept of energy. That we talked about energy in chemistry, and now we're going to talk about energy in physics. Now, why are we jumping to physics when we haven't even done chemical reactions yet? The reason is that y'all might not have noticed, but there is some good weather out there. So we can do Chem Lab. If it's snowing outside, it doesn't matter. It can be raining outside, it can be cold. But we're going to do some physics labs where we're going to go outside and we need good weather. So while it's good weather, we're going to do some physics, and then later we'll go back and we'll do bonds and chemical reactions. Those are the two things we really need to finish in chemistry. But we might do those last. We're going to do physics for a while because it just has good outside labs. We like going outside, right? Smell that sweet air of freedom. Okay, so there's two kinds of energy. One is called kinetic, and it's energy in the form of, do you already know what this is? Kinetic energy. What am I doing? I'm moving, yes. So it is energy in the form of motion. Energy in the form of motion. The amount of kinetic energy depends on the mass. If it's bigger and moving, it's got more energy, and on the speed. How fast is it moving? Now, I don't know if you've ever heard the word velocity, but it's very similar to speed. And a lot of times people say velocity here instead of speed. Okay, and the symbol for velocity is a V. Now, I don't know if you've noticed this, but sometimes people who like science are nerds. And as nerds, they will want to use a big word that sounds fancy when a little word will do. Speed and velocity are not exactly the same. Speed is how fast you're going, 55 miles an hour. Velocity has a direction too. 55 miles an hour northeast is a velocity. But because science people are nerds, they will say velocity when they mean speed because it sounds fancier. It will just be a speed. It will have no direction, but they'll use the term velocity. So just to let you know. Okay, so in this unit, we're going to do some math. So make sure that you've got your calculators. You bring them every day. You're ready to use them. But it's easy math. I'll give you everything but one variable, and you solve for the one missing one. So our first math problem is Ke, the kinetic energy, is 1/2 times the mass times the velocity squared. You get to use the squared button on your calculator. That's fun. Okay, there's kinetic energy, the energy of motion, but there's also energy that's not moving, it's stored. And you can think about that like with our battery, with chemical energy, it's not moving, but it's stored energy, chemical energy, electrical stored energy. But we're also going to talk about energy of position, and we'll be doing a lab with this tomorrow. So the formula for potential energy, stored energy, is mass times gravity times height. The amount of potential energy of a sample of matter also depends on mass and its position. Mass and its position. How far can I scroll this up? Can I scroll it to there? Is that good? Okay, so I want to tell you a true story that is where I had a real interaction with kinetic and potential energy. Remember, kinetic is energy of motion, and kinetic is potential is stored energy. So when I was in college, I went to a liberal arts college, and that we were supposed to like be well-rounded people. So it had something called a 4-1-4 semester schedule, and it's where you take a semester in the fall, took a semester in the spring, but in January you just took one class, and they want us to take it out of our major to make us more well-rounded. So one year I took Chinese, and I could say wa-a-ni, which is I love you in Mandarin. That's about all I remember of that class. And then one year I took German for travelers. Brat is bread. See, I learned a little something there. But then the next year, I took this adventure class. And the reason why is I was a college cheerleader, and the cheerleaders decided that we were all going to sign up for this adventure class where you got to hike and rappel and snow ski and then go scuba diving in the Keys. And so we were cheerleaders, and they were all excited that we would have suntans in January when everybody else was pale. They thought this was going to be great. So this cost extra because you got to go to Florida and North Carolina and stuff. And so I asked for that for Christmas, and my parents gave it to me. And I went to the very first class, and we rappelled. Y'all know what that is, like jumping with ropes, out of a 5-story classroom building. I got to go out the window, and it was awesome. I was like, this is so great, so adventuresome. But I was the only cheerleader there. So I go to lunch, and I'm like, hey, where were you guys? Y'all missed it. We jumped out of the building, out of the science building. And they were like, oh, we chickened out because that's offered through the ROTC, the Army. You didn't have to join the Army. But and we thought it was going to be too hard for us. So we all decided to take knitting with Dr. Thomas. Mrs. Dr. Thomas was from England, and they all were sitting there with their needles and their yarn. And I was like, ah. And then everyone's like, oh, we didn't tell you, sorry. And so, but I had jumped out of a building that day, so I decided I was going to stick it out. I wasn't going to do knitting. I was going to do adventure. So I had a bunch of adventures, and eventually I got to jump off an 11-story cliff. I go into downtown Atlanta, and I'll count the stories to 11 and go, I went off something that high. It was really cool. There was a lake down at the bottom. Very exciting. I enjoyed it. Well, one of the things we did after our extreme hiking and rappelling is we went snow skiing. And I didn't know how to snow ski, but and the Army doesn't pay for fancy things like skiing lessons. But I knew how to water ski, and I thought, hey, I'll figure it out. Now, most of the people in this class were really strong Army guys, athletes. There were some girls. They were all on the volleyball team on scholarship. There was not one that was less than 6 feet tall. They were 200 pounds. These were big, strong girls. And I was sort of the wimp. I know that might shock you, but I was sort of the wimp of the class. So a lot of times, the reason why people signed up for this class was to have these adventures, and they weren't going to go slow with me. So a lot of times, I did things by myself, but that was okay. I was having a great time having my adventures. So when it got to be snow skiing day, and I didn't know how to snow ski, but I didn't know how to water ski. My parents owned land on Lake Lanier growing up, and we had a ski boat, and I'm really good at water skiing. I can ski on 2 skis or even 1. It's called slaloming, and I could jump on water skis. And I thought, how different can it be? So do any of y'all snow ski? Anybody know what I'm talking about in here? See, just like how I was at your age. Well, you start off on something called the bunny hill, and it's just this little hill, and you coast down it, and you learn if you put your skis together, it's called the snow plow, and you'll stop. And to get back up to the top of the hill to do it again, there's a rope. You hang on to it, and it drags you up the hill. So I got pretty good at it. It was me and all the 5-year-olds that day. I don't think there was another person older than 5 but me, and we all figured out the bunny hill that day. And I started getting bored. I was ready to go on to the next thing. So the next thing is you ride the ski lift up to the big mountain here. And the ski lift, it's got these little seats, and they're going in a continuous loop up to the top of the mountain and down again, and it doesn't stop. So you ski up to it right here, and then it scoops you up and carries you up. And so I watched people do it for a while, and I thought, I can do this. So I skied over, and it scooped me up. And I was all excited. I'm going to do another one. And it got to the point where you're supposed to get off right here. And to get off, though, you had to jump and ski away before it clobbered you, the seat coming. And I was like, I do not know how to do this. The bunny hill did not prepare me for jumping and skiing away. I cannot do this. So I just froze. I just sat there. And then it was the next level up, about right here, and it was even a bigger jump. I mean, it was like 4 or 5 feet through the air to jump and ski. And I was just like, I cannot do this. I don't know what to do. Well, then I got to the very top of the mountain, and at the very top of the mountain, you could just stand up. The snow was under your skis, and it turns around so it doesn't clobber you. And now, I didn't know this, but I could have just sat on it and ridden back down. I didn't know that. I thought it was like Six Flags. You get to the end of the ride, you have to get off. So I stood up, and here I am at the top of the mountain, and I don't know how to ski. So my problem was physics. My kinetic energy at this point, I'm just standing at the top of the mountain, is 0. But my potential energy is max. I have too much potential energy. That's my problem. I'm at the top of a mountain, and I don't know how to snow ski. A terrible predicament to be in. Well, I look up there, and there are little bitty 5-year-old kids up there skiing. And I thought, okay, if they can do this, I can figure it out. And so I looked, and people don't just ski straight down the mountain. They go one way, then back, they zigzag. So they like ski one way, and then they push hard with one foot as they turn like that, and then they go the other way. So I watched all the little kids doing it, and I thought, I can do this. So I did it. I skied over here, I pushed hard with one foot, I pivoted, and I skied back over here. It was going great. I did it one more time. Push, turn. I thought, I can do this. I can get off this mountain. This is going to be fun. I got cocky. That was my problem. Got over here, went to push and turn, and my skis got tangled, and I got pointing straight down the mountain. And I started picking up speed fast. And I thought, oh no, but that's okay. What I'll do is I'll just put my poles under my arms, I'll crouch down low, and fall over in the snow. As soon as I did that, that makes you go really, really, really fast. So all of a sudden, I am just rocketing straight down this mountain. And at this point, I am at this next level, and up here at Tippy Top Land, there were not many people at all. But once I got to the next level, there were all these people. And I knew that if I fell or ran into them, bones were going to break. Somebody was getting a broken bone. Probably them, because I'm the bullet, they're the thing getting shot at. And they all look too nice for me to break their bone that day. So I'm sitting there, and this is where the water skiing came in handy. I knew how to keep my body weight over my skis. I knew how to lean to steer. All of that came from water skiing. And so I'm leaning to try to not hit people. Snowplow's not working at this point. We're going way too fast. And I'm like, what am I going to do? I can't just pick someone to clobber. Well, by this time, I'm down at the next level. And at this point, when I hit somebody, they're going to die. I will be killing someone. So I'm zipping down thinking, that looks like someone's grandpa. I can't kill him. That's a little girl in a cute little pink snow outfit. Cannot kill her today. What am I going to do? I knew I was going to die. But it didn't seem fair to just randomly kill someone else who's just having a nice day on the ski slopes. So then I got another great idea. I'm rocketing down here, and down here is the ski lodge, and it's made out of rock. And I think all I've got to do is not hit anybody, till I make it all the way down to the ski lodge, and then I'll just clobber myself into the rock ski lodge, and I will be the only person to die. I won't kill anybody else. This is a great idea. So here I am, zoom, 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 zipping down the hill, but a terrible thing happened. While I was messing around up here trying to learn how to ski, a line from the ski lift formed going all the way in front of the ski lodge. And they all looked way too nice to kill. So now I'm at the very bottom, and my potential energy is what? Even though I'm going really fast, what's my potential energy? 0. My position is all the way down. But what's happened to my kinetic energy? It's at max. I am rocketing. I am absolutely flying like an Olympic skier. And there's people here, and I'm going to kill me and somebody else if I run into the ski lodge now. Then I got another great idea. Over here was a mountain. Really, it was at right angles. Mountain, ski lodge, another mountain over here. And I thought, I know what I'll do. I'll just lean toward that mountain, and then I'll just go up it a little bit. It will slow me down. I will get out of this terrible situation. So I'm very excited. I'm able to do it. I use all of my water skiing prowess, and I lean really hard into it, and I start going up the other mountain. I did not understand how much kinetic energy I had. Everybody skiing down the mountain was going slower than me going up. I was the fastest person on the mountain going the wrong way up the mountain. I thought I would just go a few feet up this. No, I skied all the way up to the very tippy top and would have kept going, but there was a net to stop the snow from blowing off the top of the mountain. I crashed into it. Boom. I lay down on the snow. I am trembling all over, head to toe, cannot breathe. I am just so shocked that I'm alive at this point. Well, there are these cops. They're called the ski patrol, and they come skiing up. They're wearing all black, and they make their skis sound mad at me as they stop. And they're all yelling at me. We saw what you did, and if we see you do that again, we're taking your lift pass. I cannot speak, but I'm thinking you absolutely should take my lift pass. You should probably have me arrested. I almost killed people. And but they just kept yelling. I could not say a word. I was so out of breath and so trembling all over. And they skied away. You want cops to be helpful, not ski away. But they left, and I'm just trembling all over. And the problem is, I'm at the top of the mountain, and I still don't know how to ski. What is my kinetic energy at this point? 0. What's my potential energy? Max. I thought, oh no. But finally, I actually did have a good idea. I took my skis off. I crawled over to the side with my skis. I wouldn't even stand up. I was too terrified. Hands and knees. All the way over to the tree line, and I held on to one little pine tree, and then I'd hold on to the other one all the way down to the bottom of the mountain. Got down here, and my friends skied up from the clouds. Lisa, we didn't know you were a Olympic snow skier? How in the world did we not know this? And I'm like, I don't know how to ski. And they're like, what? But we saw you. I'm like, I didn't know what to do about the lift. I got scared and I got stuck. And they just died laughing. They're like, you're kidding. We've never seen anybody ski like that. And so what they did is they're like, we got you. We'll take care of this. So they got one guy on both sides, and we got on the ski lift, and when it was time to hop off, they just jumped and dragged me off. And we did that over and over again until I got brave enough to jump off the ski lift. And then I could ski down here and do the snow plow. I got good at it. I got good going back and forth. Well, then I got a little bored. Of course, they all left because I'm the weak link in this whole adventure class. And I got where I could go to this level, and I got to where I could go to that level. I knew to stay away from tippy top of the mountain. But I started getting a little bored, and there was another trail going the other way, like into the board off here. And I thought, well, let's try that one. I'm pretty good at this level now. Let's go the other way. So I'm going along this little trail. It's just very beautiful. Trees on both sides, these fir trees. I'm just skiing along. It's great. Suddenly, the path goes down real fast and then up. It was a jump. I'm jumping. Ah! Boom. But it was a series of jumps. So here I am jumping again. Ah! Boom. Now, the third jump, I don't understand how it was supposed to work, because somehow you were supposed to turn while you were jumping. That seems like it's impossible with physics. But anyway, it turned and I went straight. So I ended up at the top of a tree and I grabbed hold. And it was one of those fir trees, so it was going woo, and I'm holding on, snow's going everywhere. I crawled down, but this time I knew what to do. I took my skis off and I crawled from one little pine tree to the next all the way down. So anyway, that's the only time I've ever been snow skiing. It was very adventurous, and I had a lot of problems. But this is what I ended up learning, is if there is a black diamond, that means that I have no business being there. So there was a black diamond up here, but there was one right there too. So I didn't know that that trail was jumps, but someone who knew anything about snow skiing would have known not to go on that little skinny trail. So now you know, if you ever go snow skiing, stay away from the ones with black diamonds in them. They are scary. Okay, so that's our potential and kinetic energy. Now, I only tell this story to a group of young people. The reason why is one time I told it to a group of grown ladies, and one of their kids had died in a snow skiing accident on a church trip. So that's not as interesting if like your kid actually died doing this, because they're thinking, I bet it was someone who was as dumb as you going up to the top of the mountain when you don't know how to ski. But anyway, but you know, all of y'all look too young to have a kid who died snow skiing, right? Okay, but yep, that was a lady I knew. Okay, so what is work? I think y'all got kinetic and potential energy down. What is work? Work is the transfer of energy in physics through motion. Now, in our common speech, we use work for different things than that. You can say if you have a lot of homework, oh, I got a lot of work. But unless you're actually moving, then you're not doing work in the physics sense. For it to be physics, something has to move. The amount of work done depends on two things: the amount of force exerted and the distance it moves over which the force is applied. So like Winnie the Pooh down here going think, 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 he's not doing any work other than moving his hand to go think, think, think. Thinking, no matter how hard, is not work. Now there's a formula for work. Work equals force times distance. The work unit is joules. The force unit is newtons, and the distance unit is meters. Joules sounds like a diamond, but you notice it's spelt differently. And 1 joule is equal to a Newton meter, which is the amount of work done when a force of 1 Newton acts through a distance of 1 meter. Now, I always think of Newtons. I think of the Fig Newton guy. Did y'all remember that old commercial with a guy in a fig costume dancing around? I'll try to find the video and show it to you, because you need to think about the Fig Newton guy too. Also, there's a video I might show y'all where a robot is doing work and he's going work, 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 work as he's sweeping. It's about what is work in physics. So can we go on? Okay, one down. Conservation of energy, and this is where it ties into our chemistry we've been learning. Mechanical energy is the total amount of kinetic energy and potential energy together in the system. It's the kinetic energy and potential energy together. The law of conservation of mass and energy you already know. Matter and energy cannot be what? Matter and energy can neither be created or destroyed, yes. And remember, we already know that, and we already know about it with matter, and it applies to energy too. That, and they're saying which this applies to a closed system where energy cannot enter or leave. So of course, if matter or energy can leave, then you'd have less of it. But if it cannot enter or leave, then it can't be created or destroyed. That whatever you put in is what you get out. And we know that energy and matter can be converted from one to another because of our last unit we just studied on the nuclear chemistry unit. And who is this guy? Einstein, and what's his formula? E equals mc squared. And that shows that energy and matter mass can be converted in between. Okay, can I scroll? We good? Okay, now how about you? Where do you get energy? There's your clue. Where do you get energy?
Food.
From your food. So when you eat, the potential energy in the food, all the energy stored in those chemical bonds, gets converted into kinetic energy as you move. Kinetic energy of motion. So do you know that most of your food goes to keeping you warm? That your body temperature, you know, we're warm-blooded, not cold-blooded. It keeps you warm. So, but also running around, that uses your food up too. Okay, we good? Temperature and heat. Okay, so what is the difference in temperature and heat? So the words hot and cold are commonly used talking about energy of things. So it has something to do, temperature has something to do with heat. And it goes back to what's called the atomic theory of matter. All matter is made out of what? Starts with an A. We've already learned about them. There's a chart of them over there. What are those things over there called? They're elements or atoms, right? Everything is made of atoms. We already know this. They're so small you can't see them, even with an ordinary microscope. So here are some atoms and they're vibrating. If they get hot, they vibrate faster. If they get cold, what's going to happen? They're going to go slower, yes. So the particles that make up an object are constantly moving. Even if the object appears perfectly still. This little marker I have appears still, but if we could get in a little ship that could go down really small and go see the atoms, they're moving, they're vibrating. Now, they eventually would stop at a point called absolute zero. It's way, way below zero, very, very cold. Then a molecular motion is supposed to stop there. Temperature is the measure of the average kinetic energy of the atoms in a sample of matter. So what is temperature? It's just the kinetic energy, the average of it. As a particle and an object move faster, their average kinetic energy becomes more and the temperature rises. If it moves faster, the temperature rises. How are we feeling so far? Are we liking the physics so far? My first period, about half of them said they liked the chemistry better and half said they liked the physics better. Don't go yet? Okay. I can wait. Okay, you ready? All right, total heat or thermal energy is the total energy of the atoms in the material. This includes potential and kinetic. And different kinds of matter have different thermal energies. Now let me show you the application of this a little bit. Here I've got a teacup of boiling water and I got the ocean. Which one do you think has more total heat? The teacup or the ocean? What do y'all think?
What?
If you had a teacup of boiling water or an ocean full of nice cool water, which one do you think has more total heat? The boiling water has a higher temperature, but if you look at all the atoms, which one has more atoms? The ocean, right? And if you look at all the bonds, imagine if you were going to break all the bonds. There's a whole lot more bonds to break if you were going to turn them into a bomb. The ocean can be a much bigger bomb. Does that make sense to you? So it has more potential and kinetic energy. The teacup has a higher temperature, yes, but the one that has more total heat is the ocean. So if we do greater than, less than, ocean is bigger. Now, do y'all like the bird or whatever? I like Pac-Man for my greater than symbol. He wants to eat the ocean. not the teacup. That's a test question, so make sure you kind of wrap your head around that. Okay, so let's talk about heat. Heat is the thermal energy that flows from something, and it goes from something with a higher temperature to something with a lower temperature. Heat flows from hot to cold. Heat is measured in joules, and heat can be transferred. And I bet y'all already know a little about this. Okay, so here I've got a fire and a pan. I'm holding the pan, but I don't have an oven mitt, so it's starting to get hot. Does anybody know how heat was transferred here? It starts with the letter C.
Chemistry?
It's conduction.
Miss Blackburn, will you say Jaden Hamilton to me just for a moment?
Yes, ma'am.
Thank you.
Jaden. Oh, there you are, Jaden. You don't need a pass, just go. And do you know who that was? That was the front office. That was the very front office at the front of the school, Miss Brooks.
Don't know where
You don't know. Just go to the 100 hall, the main hall here. Go to the main hall and just keep walking. Do you want to go with me, Miss? Thank you so much. All right. So conduction is our first way of transferring heat. Here we're blowing the heat, and that's called convection. Now, do any of y'all have a convection oven that has a fan on it? Y'all are fancy. I don't. Miss Olivier has one, but it's supposed to cook your food better. If you have where your oven has a fan, it's supposed to cook faster. And the last one is by the sun. The sun heats by radiation. Radiation. Okay. Did y'all know those already? Conduction, convection, and radiation? Oh, I see people saying yes. I'm so glad. Okay, our next one is specific heat. Now, you might not know the words for this, but I bet you know the principle. That the amount of energy it takes to raise the temperature of 1 gram of material 1 degree Celsius. The change in energy cannot be measured directly, but they can be indirectly. Okay, so let me tell you what this means. Things don't heat up and cool down at the same rate. You know this if you've ever unloaded the dishwasher right after it got through washing. If you put your hand in there and touch everything, it doesn't have the same temperature, even though they were washed in the same water just minutes before. Some things feel hotter and some feel colder. Have you ever noticed that? That is specific heat. So if something has a low specific heat, it heats up fast and it cools off fast too. And the thing that we're going to use for our example of a low specific heat is metal. Now I have an old heavy metal guy here just because he's more fun to draw than a lump of iron. But it's not really the guy, it's not really the music, it's metal, like a spoon. If you took a spoon and held it into a fire, you would drop that real quick, wouldn't you? Because it would get hot fast and you'd let go. But once you let go and it fell, you wouldn't have to wait very long before it cooled off and you picked it up. It's because it has a low specific heat. Also, and so the spoons in the dishwasher cool off fast. The ceramic mugs are in the middle. And that's what we like about them. You can get your nice ceramic mug. It's going to heat up. It's going to keep your hot chocolate warm. You're going to enjoy holding that ceramic mug. It's not your hot chocolate's going to stay warm a good long time. And it's because ceramic has a medium specific heat. Down here we have water. Water has a very high specific heat. If you want to make spaghetti, you put that pot of water on the stove on high, it's going to take at least 10 minutes for it to heat up. But then if you decide, I don't want spaghetti, and you turn it off and leave it sitting there, and you say, I want to go to McDonald's, you go to McDonald's and come back, and that pot is still that water in that pot is still slightly warm. It takes it a long time to heat up and a long time to cool off. And that's because water has a very high specific heat. So even if you didn't know the word, you know the principle. And that's what makes us have life on this planet for one reason. There's a bunch, but that's one. Is our planet is covered with water. Other planets, when they turn to the sun, they get too hot, 700 degrees to support life. And when their planet rotates on its axis and it's facing space, it gets too cold to support life. But we're covered in water. We're the water planet. So when we turn to the sun, the extra heat all goes into the oceans, and we stay a good living temperature. And at night, when we turn away from the sun, the water gives its heat back to the earth, and it makes it where we can live. So if our planet wasn't covered with water, we wouldn't have life. We've never found another planet like ours covered in water that can support life in the universe. They're looking for it all the time. They want us to go colonize a planet, but to find one, it needs to be a rocky planet, not a gas giant, and it's got to be covered with water like Earth. And they haven't found one yet, which is a little disappointing to me as a science nerd who grew up on Lost in Space. They were going to Alpha Centauri, they were going to live there, and it's just not coming to pass. A little disappointing. Okay, so this unit is so little that we're actually going to do one more thing in this standard, but we're going to do another standard too. Okay, so right here in the standard, it says that you're supposed to have heating and cooling curves, and that is this. Oh, it's not wanting to write. Let's try to make it a little bigger and see if it'll do it. Yeah, let's make it a little smaller and see if it'll write. Let's turn it to a different color and see if it'll write. Let me do it over here. The board doesn't want to cooperate anymore. Let's see. Okay, so now I wrote with that, maybe you'll let me write over here. Okay, so that thing is a heating and cooling curve. We have temperature over here and heat over here, and remember they're not the same thing. Heat is all the energy, kinetic and potential. Temperature is the average kinetic energy of the motion of the molecules. Okay, so here I've got some ice. You're still not going to let me write on it. See if I make it bigger if I let me write on it. Yes, it is. Okay, there I've got ice. Here I've got water. And here I've got steam. With my ice, it's way below zero. I heat it up to the point of freezing or melting. And this is 0 degrees. And even if I add more heat, the temperature doesn't change. If you have a glass of ice water, it's always 0 degrees until every piece of ice melts, and then it'll start heating up again. Then I heat up my water, heat it till it's boiling. And then once it starts boiling, even if I add heat, it doesn't get hotter. All the energy goes into making it boil. And then if all the water is boiled, let's sit down. If all the water has boiled, then and it's all gone, then it'll become steam and it can get hotter. So if you have some water boiling and you want your food to cook faster and you turn up the heat, it does not change the temperature. It just makes it bubble a little faster. So that is a heating curve. Now, when you add heat and it heats up, it's called sensible heat. So I'm going to change my color here. Maybe you should too. So sensible heat is when you add heat and the temperature goes up. I think I said that wrong. I was thinking about changing my color too much. And those places where it's ice, water, and steam. Where it's latent heat, let's be, what's a good color? Gold. Latent heat is where you add heat and the temperature doesn't go up. So that's here where it's boiling and here where the ice is melting. Now this is new to the standard. When I very first started teaching physical science a long time ago, this was something that was taught in physics but not physical science. But now it's in your standard. So they've made it a little bit harder, but it's not too hard for y'all. Don't you think you can understand this? Though ice water is always 0, boiling water is always 100. Or ice water in English is 32, and Fahrenheit boiling is 212. Until it's all gone through a phase change, and then the temperature will change. That's not too bad, is it? Okay, so last idea. And this last idea, I think you already know. And so I'm going to see if y'all can tell me the answer. This This is about the states or phases of matter. The states of matter. And I think y'all already know about solid, liquid, gas, and plasma, don't you? Let's see if y'all can figure it out. Which one, solid, liquid, gas, or plasma, has a crystal lattice, a definite shape and volume, lower heat and energy, and can only vibrate? Which one do you think that is? Solid, liquid, gas, or plasma? It is solid, yes. Y'all are great. Okay, so now we have liquid, gas, and plasma to choose from. So solid is my ice right there, okay? The next one, molecules are free to move. They take the shape of their container, but it has a definite volume.
It's liquid.
The answer is liquid. I heard it. So here's my liquid. See how it takes the shape of the container, but it has a definite volume. It doesn't fill the container. Okay, now we're down to gas and plasma. Molecules are free to move faster. They take the shape and fill the container, and they have a high energy or heat.
Gas.
Gas. Gas. See, I knew y'all already knew this. So that's my balloon. And now, of course, plasma is the last one. And that's in lightning. It's in the stars like our sun. So there's our plasma up there. Okay, now the next thing is called the gas laws. And you might not, if you've had chemistry, you already learned this. But even if you haven't had chemistry, I think you already know this because you've lived your life and you've been observing things. Okay, so there are some laws, and the first one's called Charles's Law, and it's that if the temperature goes up, what happens to the volume? So look over here. I've got a hot plate, and I've got an Erlenmeyer flask with a balloon on it. If I increase the temperature, will the balloon get bigger or smaller?
Small.
It'll get bigger.
It's going to get bigger. You heat it up and the temperature goes up. So if the temperature goes up, the volume goes up. Now if I take my balloon and I go stick it in a freezer, is it going to get bigger or smaller? It's going to, so if the temperature goes down, the volume goes down. And there's a mathematical equation that the volume over the temperature equals the volume over the temperature. So that is Charles's law. Okay, the next one, boils. Okay, imagine I have a balloon and I put pressure on it and squish it really hard and my hands are big and I'm really strong. Will the balloon get bigger or smaller when I squish it?
Smaller.
Smaller. So if pressure goes up, volume goes down. I told you you would already know these. If pressure goes down, if I put my balloon in a vacuum, what's going to happen? It's going to go up. Pressure down, volume up. And the formula for that is pressure times volume equals pressure times volume, Boyle's law. Okay, Dalton is that pressures add up. You can add them up. So let me explain it to you. Here I've got water and some oxygen in this flask. If I stick a needle in it and pump in some nitrogen, will it have a higher pressure or a lower pressure?
A higher pressure.
It's going to be higher because pressures add up. Greater the density, I think I just wrote greater here. Yes, the greater the pressure. So no matter how many you have, the more pressures you put in there, they add up. Now the next one is called, it looks like it says Gay-Lussac, but it's French, and I think it's pronounced Guy-Lussac. I know a little Chinese and a little German, but I don't know any French, so I don't know. Maybe some of y'all who speak French could help me out there. But I bet you know this one too. This is pressure and temperature. So imagine I have a can of air, not Coke, over a fire. As I heat it up, will the pressure in that can go up or down? Up. Somebody said it up. It's gonna. So if the temperature goes up, the pressure goes up. If I go and take that hot can of air and go put it in a freezer, then the pressure is going to go down. So that is Gay-Lussac's is right here. The ideal gas law just says that the factors are all connected. Temperature, pressure, and volume are all connected. And the number of particles, it's all connected. And there's a law called the ideal gas law, PV equals 1 nRT. Okay, last idea, and it's Bernoulli's principle. Okay, so there was a guy, Daniel Bernoulli, not Daniel Principle, and he figured out something that all of that stuff we just talked about makes sense. It all is very like, yeah, that's logical. That spoons heat up fast, they cool off fast. That if you heat up a balloon, it's going to get bigger. But this is not intuitive. Everybody blow in your hand. Does it feel like a high pressure or a low pressure in your hand? The answer is low. But to me, it seems like it's high, so it's counterintuitive. It turns out that if air or liquids, air or water, moves fast, it causes a low pressure. That's Bernoulli's principle. It's how airplanes fly. It makes more sense to me with airplanes. Airplanes have curved wings. The air underneath, it can just go straight. But the air that goes on top spreads out to get over that greater distance of the top of the wing. When the particles spread out, it causes a low pressure on top, a high pressure on bottom, and it creates lift. And planes, even though they're big and heavy and full of people, can fly through air. Isn't that amazing? You might have seen this before if you have a shower curtain instead of a shower door. If you have a shower curtain, you turn on the shower, you have a fluid moving fast, it causes a low pressure. Does your shower curtain get blown out into the bathroom or in on you? Anybody have a shower curtain? It goes in on you, and it's terrible because it's cold, because your brother already took a shower, and it's got cold little drops in it. It comes in on you, and you're like, don't touch me. That's Bernoulli's principle. Fluid moving fast makes a low pressure, which sucks that shower curtain in on you. We're going to do some fun little experiments with it. I'll do some demos, and you'll get to see that it really is out there in the world, but it's sort of counterintuitive. So that's Bernoulli's principle. So that is this unit. What do you think? Not too bad? Good. All right. Like, share, subscribe. Science is great.